That looks like it's working. Okay, great. Thanks very much for the invitation to speak today. It's really great to be here. Also, thanks very much for whoever organised the British rain that we had this week. It's really made me feel at home. So thanks for that. So yeah, this talk is in 4 parts. I'm going to start by talking about self-supervised reconstruction and why it's important. And then I'm going to take what might seem like a short digression to talk about a method from the denoising literature called noisier to noise. And I'm going to explain the work that we've done, which is using noisier to noise for reconstruction tasks. And then finally, I'm going to focus on a recent bit of work, which is all about self-supervised learning in the low SNR setting. Okay, so the data acquisition process in MRI is inherently slow. And this is a real problem for if we need high spatial resolution, such, for example, if we need to resolve a fine structure like the cartilage in a knee, or we need high temporal resolution, for example, if we're doing dynamic imaging. We can accelerate acquisitions by subsampling. And we can do this because the acquisition time is approximately proportional to the number of readout lines. So if we subsample by a factor of 4, this is around 4 times faster. So those of us that are interested in reconstruction algorithms, we're trying to develop methods that take a subsample case space as an input and pass it through some algorithm, F with parameters theta, to give us some kind of estimate of the fully sampled case space, as if we'd never subsampled at all. So we can also think of this as in the image domain. So a subsample case space will look something like this in the image domain, like an aliased image. And our goal is to construct some kind of algorithm that removes the aliasing so we get a nice, clean diagnostic quality image. So this talk is all about how we choose F. So until about 2017, the dominant way of choosing F was to have a hand-picked model. So for instance, motivated by the theory of compressed sensing, a common thing to do was to assume sparsity. So for example, we know that if we do some kind of transform to our image, as shown here, we might do a wavelet transform, and there's lots of zeros there. So we can use that assumption to reconstruct our image. But more recently, something that's become increasingly popular in the community is to use data-driven reconstruction with deep learning. So in this case, we don't pick the model ourselves. What we do is we use data to learn a model. So there have been a very large number of architectures proposed for doing this kind of thing. I've highlighted a couple of particularly well-known ones at the bottom here. But this talk is actually, I'm not going to go into the details of any architectures at all. I'm not going to talk about what we're training. I'm just going to talk about how we're training. So everything is going to be network architecture agnostic. This talk is about the training method. So how do we train normally? Well, what we normally do is fully supervised learning. So we assume that we have a lot of fully sampled training data. And then what we do is we simulate subsampling. So we retrospectively subsample with a mask that we generate ourselves. And then we train our neural network F to map from subsampled case space to fully sampled case space, or if you like, the alias image to the clean image. So this is all very well, but there's a bit of a kind of chicken and egg thing going on here, right? Because where the egg is, the whole reason we need a network in the first place is because fully sampling is difficult or maybe even impossible for our desired spatial temporal resolution. And the chicken is we need fully sampled data or we can't train network, or we can't train the network, right? So this is a bit of a tricky situation, so that if we're going to do this type of training, at some point we're going to need to fully acquire case space, which may not always be feasible. So more recently, there's been a push towards self-supervised learning methods. So the whole idea of these is that the training data is itself subsampled. So at no point do we need to require fully sampled data for training. So this is really great because we can just use standard protocols. So we could just subsample in our normal way and then use all that data to train our network. So what do we want from a self-supervised learning method? Well, Firstly, we'd want it to perform kind of similarly to fully supervised training, ideally. We'd also want it to work for any network architecture. There are so many that are being proposed. It feels like every day there's a new architecture being proposed for ML reconstruction. We don't want a method that's constrained to particular architectures. We also want the method to be robust. So I'll go into a bit later. I'll go into what we mean by robust to what. But this is a kind of wish list for how we would want a self-supervised method to behave. So a common way to do this is by some authors from Yaman et al. From 2020. And this method is called self-supervised learning via data undersampling. And the way that SSDU works is that we take our subsampled measurements and then we partition our measurements into two. So by partition, I mean that everything in the measurements either goes into the top subset or the bottom subset, but not both. So after we've done this partitioning, what we do is we take one of the partitions and then we train our network to map to the other partition. So essentially, we reserve some of k-space for the network input and some of k-space for our self-supervised loss. So I'm going to talk quite a lot about this method in this talk. So if it's not immediately clear why this makes sense as a thing to do, hopefully it will become clear as the talk goes on. So our contributions during my postdoc with Mark is that we have shown that SSDU is actually equivalent to a method called noisier to noise. So noisier to noise was published at about the same time as SSDU, but was applicable to denoising, self-supervised denoising. And this has a number of consequences. Firstly, it means that we can prove SSDU. So for the first time, we can show that SSDU does actually recover the clean image. Secondly, it suggests a number of modifications to SSDU, which we find significantly improves its performance and also robustness to hyperparameters. Finally, we'll talk a little bit about how this leads to a natural extension of SSDU that means it's able to deal with low SNR measurements. So this part of the talk, we're gonna take our reconstruction hats off and put denoising hats on. So we're just going to talk about self-supervised denoising. So this is the case where I want to remove noise from an image, and my training data only has noisy images. I don't have any examples of clean images, only noisy. So it's closely related but different. So the method that we've been focusing on is called noisier to noise. And the way that noisier to noise works is that we take our noisy data as shown, our noisy image as shown on the left here, and then we add more noise to get a further noisy image. And then we train our network F to map from the further noisy image to the less noisy image. Some of you may be familiar with the method noise to noise, which maps from a noisy image to another independent noisy image. This has the benefit over noise to noise is that we don't need paired images. We only need one image of each type. So just add further noise to that image. And then once we've trained our network, we take our noisy image and then we pass it through our network with a linear correction that I'm going to explain in a minute, and then hopefully get a nice clean image out at the end. So to explain a little bit about how this works and get a feeling for it, I'm going to need to define some things. So let's define the noisy image to be Y, and the ground truth clean image to be Y0, and the noise to be N. Here I'm using the subscript T to index the training set. So T runs from 1, 2, 3, 4 up to the number of images in the training set. So N here, just for simplicity, we're assuming that N is Gaussian with 0 mean and some standard deviation sigma. And then we need to generate our noisier image. So to get a noisier image, we take our noisy image Y, and then we add more noise, which we're calling N tilde, which is also Gaussian with 0 mean and some standard deviation scale by alpha. and then we have some kind of, and then we have a loss function, which is the difference between the output of the network if we pass y tilde through it and y. So the network acting on the noisier and the difference between the y, difference between the noisy. So we can actually be very precise about why this works. And to do this, we characterize y and y tilde as instances of random variables. So when we're doing this, what we're saying is that our images are drawn from a distribution, and we use random variable terminology to define that. So we say y is an instance of the random variable capital Y, and y tilde is a random instance of the variable capital Y tilde. So in order to prove a method like this, we need to think about how we're going to characterize the distributions of y tilde, and y naught, which is the clean image. So last time I showed you, on the last slide, I showed you the loss, which was between f of y tilde and y. And here we do exactly the same thing. So when we're talking in terms of random variables, we replace the sum with an expectation. And we note that we need to have it conditional on y tilde, because y tilde is the input to the network, so it's the information that we provide. So if we minimize this loss, then it's straightforward to show that the parameters that a network f with parameters theta star q according to this satisfies the following expression, which says that the expectation of y naught given the noisier image y tilde is equal to something that depends on the output of the network, and alpha, which was how we scaled the noise when we introduced further noise, and y tilde, which is the noisier image. So in other words, at inference, what we do is we take our trained network and we do this correction and we get our clean image. So this is the linear correction that I alluded to on the last slide. So thinking kind of more heuristically, why is it that noisier to noise works? The reason this works is because it's not possible for the network to tell the difference between the original noise and the further noise. So that means that it learns to remove both in expectation. So what happens at training is that I give a network this augmented input, in other words, the noisier, and I'm trying to get the network to recover the singly noisy, but it's not possible for the network to distinguish between the original noise and the further noise. So it removes both in expectation because it doesn't know which is which. So this is a really important point that I'm going to come back to later in the context of reconstruction. So I'm going to put a pin in that to remind everyone to keep that in mind for about 5 or 10 minute slide, 5 or 10 minutes time. Okay, so now we're going to talk about how we translate this noisier to noise method to reconstruction tasks. So as I mentioned earlier, we have shown that this method noisier to noise is actually one and the same with the method SSDU. The difference between noisier to noise and SSDU is that while noisier to noise corrupts noisy images with further noise, SSDU corrupts subsampled case-based data with more subsampling. So as we'll see shortly, we can use a very similar kind of setup to how we proved, how we demonstrated the proof of noisier to noise earlier, to prove that SSDU is correct in expectation. It also implies that SSDU benefits from a certain weighting in the loss that compensates for the sampling and partitioning densities. And it also tells us what type of sampling set partitioning we should be doing. Okay, so this is going to be exactly the same as the definitions that I showed you before, but for reconstruction instead of denoising. So remember before we had our noisy, which was y naught corrupted by Gaussian noise. And this time it's y naught, which has been masked by some matrix M. So this is just a diagonal matrix that has ones where we sample and zeros where we don't. And I'm using the subscript omega t to be the sampling set. So if the sampling set contains an index, that means it's present in the mask. So the noisy is actually subsampled in this case, and then the noisier is more subsampled. So we define our y tilde in this case to be the noisy corrupted by more subsampling. And then the loss is exactly the same, apart from I've included this something here, which is a weighting matrix, which turns out to be quite important in a minute. We could have done that before in the noisiest to noise as well, but there's actually no reason to do it. But when we're doing variable density subsampling, it turns out that it's good to compensate for the variable density with a certain weighting, as we'll talk about in a minute. So what does this look like in practice? So I'll just walk us through this. So we start with our subsampled data, and then we generate another mask. We multiply that mask by the subsampled data to get a further subsampled case space. Then we pass that through our network to get an estimate of case space, and then compute the loss between the output of the network and the subsampled training data. So this may not be immediately clear that this is exactly this method SSDU that I spoke about earlier, but it turns out that if you choose a particular loss weighting, in particular this one, which is 1 minus the second mask times the first mask, then it does recover SSDU exactly. So to see how this works, so let's say our measurements are omega, and then our further subsampling is lambda. If we wanted to partition our omega, we can do this purely with lambda by saying that everything that's in omega but not in lambda goes into the top subset A, and everything that's in both omega and lambda goes into the bottom subset B. So that means that further subsampling exactly defines a partition, exactly the way that SSDU works. And if we were to write this down in terms of the mass, we get the top subset has this mask, and the bottom subset has this mask. So here the top line is exactly the SSDU loss, and if we put in our expressions for MA and MB into the line below, then we see that we get exactly the noisier to noise loss, just with that particular loss weighting function that I mentioned, the 1 minus m lambda m omega. So continuing on this idea, we can actually use the kind of noisier to noise machinery to prove SSDU. So as before, our loss function looks like this, and we do a similar thing to what we did to noisier to noise, which is we say these are instances of random variables, which are defined below, and we replace the sum with an expectation. And this allows us to characterize the distributions of y tilde and y. So our main result from our preprint is that a network that minimizes that expression star satisfies this expression, where this looks possibly a little bit messy, but I'll show you what it means on the next slide. So it's 1 minus some matrix K, where K is dependent on the sampling probabilities, and then 1 minus m lambda m omega, which is the mask of y tilde, multiplied by f theta star, so the train network minus the expectation. So if we assume that 1 minus k is invertible, which gives us some mild constraints on the way that we sample and partition, then this expression simplifies to this. And all this does, it tells us that the tuned f correctly estimates k-space in expectation in regions not sampled in the input in y tilde. The reason it's for those entries not sampled in y tilde is because of the 1 minus m lambda m omega out the front. So it tells us that the network will recover everywhere correctly, apart from the information that I've given it in the first place. This sounds like it might be a bit of a problem, but it actually doesn't matter because we already know y tilde. So the network will take something like this, a y tilde as its input, and then learn all the dark patches. So it doesn't also learn to map to itself, but that's okay because we can overwrite the y tilde so that it learns everywhere in expectation correctly. So do you remember when I first presented SSDU, I showed partitioning like this. So the original sampling was in 1D and the partitioning was in 2D. So this is how it's originally suggested in the SSDU paper. But now I want to recall this pin that I mentioned earlier and say, do you remember the whole reason that noisiest noise works is because the new noise is the same distribution as the original noise. So for this means that the new subsampling needs to be of the same type as the original subsampling. So this is just that rather than doing partitioning like this, we should do partitioning like this, where we partition in columns, just as the original data was. Okay, looking back at this expression which came up in the proof, does this 1 minus k have any redox? Because we said that if it's invertible, then we can just multiply it out. But this actually tells us something about the sensitivity of the network. So if 1 minus k is small, it means that our network is more sensitive to errors in those regions. And the reason for that is because if you imagine you've got subsample data, and let's say towards the periphery of k-space, you might not have many sampled examples of that in a test set, in a training set at all. Maybe it only occurs 1 in 100 times. Then that means we need to tell our network at training that it's more important to make sure you get that right when it does come across one. So that's exactly what we propose to do. So rather than doing this loss function as I originally suggested, we actually propose including a 1 minus k inverse a half, which means that we can do exactly the same proof as before, but the 1 minus k cancels so that our network is not as sensitive to errors in those regions. We find, as I'll show you shortly, this makes quite a substantial difference in the performance of the method. So to evaluate this, we used a widely used data set, which is the fast MRI data, and we use the multi-core data of the brain part of it. We use a very commonly used architecture, VARNet, which I'm not going to go to in any details here, but it's one that's quite widely used. And then for our sampling, we sampled in 1D or 2D. So in some cases we did column-wise, just as I've shown you so far, and in some ways we did 2D, and we also did 2D sampling like this. And then for each of these, we partitioned in 2 ways. So we either partitioned in columns or we partitioned in 2D, like the original SSDU. And we also did the same with the 2D image. So we partitioned that in columns and in 2D. So this shows, so I'm just showing a kind of subset of the results for the sake of this talk, but there are more different acceleration factors. And we also did it on the knee data as well in the preprint, which I'll mention at the end of the presentation. So what we found is that, so 2D part, so this is for the 1D sample data. What we find is that 1D partitioned SSDU, which is shown in green, considerably outperforms 2D partitioned SSDU, which is the way it was originally proposed. And also K-weighted, this K-weighting gives another further performance improvement. So it's only about 1.5% worse than if we were doing fully supervised training. And I will see on the next slide that qualitatively the reconstructions are very similar. I've also included something called unweighted noisiest noise, which is when that loss function, in the loss function, remember there was that weighting matrix W. If we just set back to the identity matrix, and I called that unweighted noisier to noise, just for the sake of completeness, we found that it didn't really, this is kind of a more obvious way to implement the noisier to noise for reconstruction from the original paper. But we find that it didn't work very well in practice, so I'm not going to talk about it anymore. So having a look at the actual reconstructions. So on the left is the fully sampled reference, and then next along is is what we get when we do fully supervised learning. So this is where we let our network have access to fully sampled training data. And then next along is 2D partitioned SSDU, so how SSDU was originally proposed. And then next is the same, but with 1D partitioning instead of 2D partitioning. And we see that there's a reduction in aliasing compared to 2D partition SSDU. And then finally, on the furthest right, we have the K-weighted version, where we compensate for the variable density. And we find that this one is the most similar to fully supervised training. And yes, qualitatively, the differences are quite marginal. So I spoke about the fact that we should partition in a way that, so that if we partition in columns, we should also, if we sample in columns, then we should also partition in columns. But I haven't spoken about how much we should partition, like how much should be in each of the subsets. So this is just a test to see how sensitive each of the methods are to how much we partition by. So the NMSE is the test set normalized mean square error, and the horizontal axis is how aggressively we subsample with our second mask. And what we find is that the 2D partition SSDU is very sensitive to how aggressively we subsample with the second mask, whereas the two proposed versions are much more robust, especially the K-weighted version. So, for example, so if we look at so each of these shows the same image reconstructed with the same method, but for different acceleration factors of the second mask. And the highlighted box shows when it performed best. And you can see that the 2D partition SSDU on the left, even for changes of 0.2, there's considerable streaking in the reconstruction. Whereas for our K-weighted 1D partition SSDU, there's a very similar performance across the range of 1.6 to 6. So it's far more robust to the partition, to how much we partition by. So we also did experiments where we took where we assumed that the original data was sampled in 2D.
Transfusion. Trauma bay, bed 2. Your attention, please. Your attention, please. Code transfusion. Emergency, trauma bay, bed 2.
So we did another experiment where we just assumed that the data was originally sampled in 2D, as shown at the top. And I haven't included the K-weighted version for brevity, but what we find is in this case, it's better to partition in 2D than in 1D. So you can see that the 1D partition version has these kind of horizontal streaking artifacts, whereas the 2D partition version is very close to fully supervised. So this tells us that we should be matching the type of partitioning to the type of sampling. So to summarize this section, we have shown that SSDU is intimately connected to something from the denoising literature called noisier to noise. And we've used this to prove that SSDU is correct in expectation. And we've also suggested a couple of modifications of SSDU. Firstly, that we should match the type of partitioning to the type of sampling. And secondly, that we should introduce this K weighting, which compensates for the variable density. And we found this made a substantial difference to the performance of the methods. Okay, so I'm just going to talk very quickly about more recent work that we've been doing, and this is still a work in progress. But the whole idea is that we've essentially assumed so far that there's no measurement noise, which we know, of course, that there is. Everything we've been doing is dealing with aliasing and not the noise. But noisier to noise offers a very natural way to extend this self-supervised framework to account for noisy measurements. So yeah, so a quick bit of motivation. So if we just do SSDU and artificially add noise and see how it performs, we can see that there's clear visible noise as we increase the measurement noise. This is not a surprise, right? We haven't done anything to remove the measurement noise, so it's going to be present in the reconstruction. So this is our proposed method, which we called noise robust SSDU. And this is almost exactly the same as the flowchart that I showed you earlier, apart from this section. And what this does is that, so we still take our subsample data and we subsample it more, and then we add more noise. So we only add noise to the parts in the further subsampled case space. So what we end up with is a case space that is both further subsampled and further noisy. And then we train our network to recover the singly noisy, singly subsampled from the further noisy, further subsampled. And we can say something similar theoretically about how this works. So the loss function here is slightly different from before because we need to train the network to map to itself as well. Otherwise, it's not going to learn to remove noise. So it's m omega instead of 1 minus lambda m omega. And if we train with this, also, yeah, it's just to emphasize that the y tilde here is further subsampled and noisy, whereas before it was just further subsampled. And if we do this, then the expectation of y naught is related to the network with this expression. So also emphasize that this y naught is not just the fully sampled image, it's the clean, noise-free, fully sampled image. So this is a sum of a part which is just the additive noisier to noise correction that I showed you earlier in the context of just denoising. And there's also a part, the second term, which is just plain old SSDU, which doesn't need a correction. So this experiment shows the mean squared error on the test set and how it performs as we increase the measurement noise. So the black dotted line, which is our best case baseline, supervised to clean, what we've done is we've given our network noisy subsample data and trained it on clean, fully sampled data. So this is the best we could possibly hope for our method. So if we just take SSDU and don't do any denoising, then we get this green line. And then there's also a method called noise to recon, which came out a couple of years ago, which has it's a comparative method that has similar principles to what we're doing, apart from they add the noise in the image domain. And we have found that our method considerably outperforms this method. So our proposed method in the dark blue line is only about 2% worse than as if we had access to clean, fully sampled data. And qualitatively, so on the left, we have the reference again, and the next along is our best case scenario where we trained it on clean, fully sampled data. And we see that SSDU to noisy and noise to recon SS still clearly have some noise present in the reconstruction, whereas our proposed method is qualitatively very similar to the best case baseline. Okay, to wrap everything up, the main takeaway from this is that we can understand this widely used self-supervised method, SSDU, as a version of noisier to noise. And this means that we can prove SSDU and that we can improve its performance by modifying it. And we also find that it improves its robustness to hyperparameters. And it gives us a natural way to extend SSDU to noisy data. So a couple of things for future work. These self-supervised methods have introduced further hyperparameters. Firstly, we don't know how much we need to subsample by. We showed that our method was more robust, but we still don't have a way of automatically selecting that partition, which would be a really powerful thing to be able to do. And there's also how much of the further noise we add in the noise robust version is still just something that we had to pick by hand. But if it's possible to have an automatic tuning method, that would be really great. So it's something we're planning to look into. Related to this is this idea of zero-shot learning, where it's assumed that you don't actually have access to a training set at all. All you get is one image, and then you can train a network to recover clean images just from single example, and they've shown the authors of SSDU have shown some pretty impressive results where they do a version of SSDU with an automatic stopping criterion. So that's something that could complement the work we've done so far as well. Okay, so thanks very much for listening. If you want to read the preprint with all the gory details, the QR code is there, and also our code is available on GitHub if you want to try it yourself. And thanks to our funders, and thanks to Mark for his supervision. Thanks very much.
Hey, you want to stop recording here?
Oh yeah, good point.
All right, we'll open it up for questions. Are there any questions from the audience or online for Charlie?
Stop this.